So, hello everyone. Today we will be starting the next lecture, that is oxygen transfer from bubble to cell. So, basically this is extension of gas liquid mass transfer. So, if you remember the last lecture we discussed mass transfer theories, particularly this molecular diffusion and film theory. So, molecular diffusion, the driving force is concentration gradient, and for film theory the driving force is difference in the concentration. And what are the application of mass transfer in bioprocessing, particularly in the aerobic fermentation? It required oxygen, and oxygen is coming in the gaseous form, and it should, the gas are formed in form of bubbles, and from bubble it should go to the cells. Next is in the immobilized enzyme reactors. Once it is immobilized, your substrate should diffuse in, as well as your product should diffuse out. In case of liquid extraction, we have already discussed that this the solute must diffuse through a thin solvent film between two immiscible liquids. So, if you remember when we discussed mass transfer across the phases, then we discussed there is a interface, and surrounding the interface there is a boundary layer. It can be either side or it can be both the sides. Apart from immobilized enzyme, there can be pelleted cell culture. Then they also face this intraparticle diffusion or intrapellet diffusion. So, these are the broad application. So, in that immobilized enzyme catalysis, partly we have discussed in the applied enzyme catalysis module. Here we are mostly going to discuss on this aerobic fermentation, and our focus will be on the aeration as well as agitation or mixing. So, today we are going to see what is aeration, then how oxygen transfer takes place from air to the cell, and then what are the factors affecting the oxygen transfer. The aeration, as the name suggests, the process of introducing air to increase oxygen concentration in the liquid. It is going from gas phase to liquid phase. Now, it can be done by performing bubbling air through the liquid, by sparging the liquid into air, or agitating the liquid to increase the surface absorption. So, mostly we will be focusing on aerating the bubble, that is mostly comes under the aeration, and this agitating the liquid comes under mixing. So, this is the gas liquid mass transfer in the bioreactor. So, as we are saying, this is a mass transfer. So, there should be transfer of nutrients from aqueous phase into microbial phase. And what other transfer is required? Should be requirement of oxygen transfer as well, particularly in the aerobic fermentation, and this process is more complex because of the poor solubility of oxygen in the liquid medium, while the nutrients are much more soluble in the liquid medium. Typically, spurgers are used for the oxygen transfer. Now, when we are saying oxygen mass transfer, means there should be two terms. One is oxygen transfer rate, that is called OTR, oxygen transfer rate, the rate at which oxygen is delivered into the biological system, and second is oxygen uptake rate, OUR, the rate at which oxygen is utilized by the biological system or microorganisms. In addition, there is one more term we will be discussing, critical oxygen demand, the rate at which it is utilized by microorganisms. So, this is linked with oxygen uptake rate or oxygen utilization rate that we will be discussing in the next slides. So, typically this oxygen transfer rate at a steady state, it should be equal to the oxygen uptake rate, and when this utilization rate is high, it means the anaerobic conditions prevails in a bioreactor. And what is the typical flow rate of air? It's huge in huge quantity, it's about 0.5 to 1 ppm volume of air per unit volume of reactor per minute. So, it requires huge quantum of air supply. So, aerobic fermentation, the primary method for production of most of the metabolites, and the challenge here is the poor solubility of oxygen. Typically, if you just see the solubility of oxygen in the pure water is 8 milligram per liter, while at the same time if you just see solubility of sucrose is 600 gram per liter. Further, there are environmental factors, the like increasing the temperature or concentration of other solute further causes decrease in the oxygen solubility. So, we will see this solubility of oxygen follows the Henry law. So, we will quickly have a look at what is Henry law. So, what it highlights that the supply of oxygen is a rate limiting state, particularly in aerobic fermentation. Now, Henry law, as I was discussing, it says solubility of oxygen is directly related to the partial pressure. So, it says solubility related to partial pressure divided by Henry constant, and partial pressure is defined as total pressure into mole fraction upon H. This is partial pressure, Henry constant, this is a mole fraction, and Pt is total pressure. So, now when we are supplying oxygen from the air, what is the mole fraction in the air is 0.21. That is why when you are doing aeration, of course, only 21% is the air, and accordingly the solubility varies. So, let us say if you are supplying the oxygen through air and the solubility is 9 milligram per liter, and when you supply the pure air, what will be the solubility? So, let us say C star is given as 9 milligram per liter, this is equals to total pressure, assume 1 atmosphere, we assume Pt as 1 atmosphere constant value. So, it is 1 into YAG 0.21 divided by Henry constant H. So, from here we can get the value of Henry constant as 0.21 divided by 9. Now, if I want to calculate the constant solubility when I am supplying the pure oxygen means mole fraction is now 1. So, C star will be total pressure 1 into 1 divided by Henry constant. Henry constant is 0.21 divided by 9. So, this will be coming out to be 43 milligram per liter. So, if one can supply pure oxygen, the solubility of oxygen can be enhanced, but again the challenge is the availability of pure oxygen on installing a separate plant to separate pure oxygen from the air. Now, when we are talking of the mass transfer, first we will see the oxygen transfer rate OTR part. So, oxygen transfer rate per unit volume is defined as KLA CAL star minus CAL. CAL is saturation or equilibrium concentration, CAL is actual oxygen concentration in the broth or media, A is the interfacial area and CAL star minus CAL is the driving force or difference in the concentration. So, we have already discussed this oxygen solubility is very less, so close to 8 ppm, and typically air sparging is done to maintain the oxygen supply. Now, if you want to increase the oxygen transfer rate, if you just see this expression, first is we have to increase the KL, either you can increase the KL, you can increase the A or you can increase the CAL star to increase the value of Ne, right. So, what is objective here? To optimize for efficient gas liquid mass transfer due to this low solubility of oxygen, small driving force, the difference is small, and uptake rate is very high. That we will be discussing the specific oxygen uptake rate by microorganisms in the next slide. Further, it is important that depending on the particular species, that this is a microbial cell, in microbial cell which type of microbe is this, whether this is a animal cell or plant cell, the oxygen demand varies. Now, whether it is in growth phase or stationary phase. Further, because this oxygen is also utilized in the stoichiometry reaction, or you can say carbon metabolism. So, what is the carbon source that also utilizes the oxygen requirement. So, oxygen uptake, if you want to see how oxygen uptake varies, that is increase in the cell concentration X and change in the specific oxygen uptake rate. So, oxygen uptake rate is defined Q naught is Q naught into X. This is the oxygen uptake rate. So, if I want to increase the oxygen uptake rate by if there is more biomass, or this is the characteristic of a particular microorganisms specific oxygen uptake rate. So, here you just see specific oxygen uptake rate Q naught and with the concentration how it varies. So, with increase in the dissolved oxygen concentration, it increases and reaches to plateau. You just see a concentration point that is called C critical, at which the Q naught is independent of dissolved concentration or it reaches to saturation value. So, what it says, critical oxygen concentration, it is needed to avoid oxygen limitation, and the typical value is 5 to 10% of air saturation, and further C critical also varies for different organisms. Effect of dissolved oxygen, as you see the x axis is the effect of dissolved oxygen. So, if CAL is greater than C critical, you will see the Q naught is constant, and if it is less than C critical, typically it is a linear here. You can just see the linear profile. Further, as I discussed in the last slide, there is the effect of carbon source. For example, oxygen demand is higher with glucose than lactose and sucrose. So, this depends on the degree of reduction as I have discussed earlier. So, depending on the degree of reduction, there is a requirement of oxygen. If you remember in the stoichiometry, based on by balancing the degree of reduction, we are able to calculate the oxygen requirement. For example, if you are growing penicillin on glucose, the Q naught value is 12 millimole per liter into hour, but if I am growing on sucrose or lactose, its value is almost half, 5.5 to 6.1 millimole per liter per hour. So, in addition, as I told, it varies by organisms. In fact, this microbial cell have more oxygen requirement as compared to plant and animal cells. So, this part we need to remember that typically CAL concentration of dissolved oxygen should be greater than C critical to ensure optimal metabolism. So, this is the table, you can see these are list of various microbes and what is their Q naught value and oxygen uptake rate. So, Q naught value is given in the millimole per gram and also millimole per unit cell, and typical value of, if you just see the capital Q naught is in the range of starting with the 5, it is going up to 40 for the Saccharomyces cerevisiae producing ethanol. But if you just see the Q naught value for the plant and animal, it is much lesser than that of microbial cells. Now, let us go ahead with the transfer of oxygen from the gas bubble to the cell. So, this is the gas bubble. So, you can see from here gas bubble and to the cell, we have divided into 8 different steps, 1 to 8, 1, 2, 3, 4, 5, 6, 7, 8. What is the first step? The transfer from interior of bubble to the gas liquid interface. Then second is movement across this interface, it is crossing this interface. Third, that is the most important, at the interface there is a boundary layer or the liquid film. Then it has to diffuse through the stagnant liquid film surrounding the bubble. Then now from gas it has come to liquid, so it has to transport through the bulk liquid. Then fifth is again cell and there is again a boundary layer or the liquid film, so it has to diffuse through the stagnant liquid film. Then it has to cross this interface. 6 is the movement through the cell interface. Then 7 is the, if cell or the flock, clumps or solid particle, then it will diffuse inside, and finally it will transport to the cytoplasm to the site of reaction where oxygen is required. So, you just see oxygen transfer phenomena for all 8 steps. For the first step, gas phase transfer inside the bubble, it is a first process. Gas phase crossing the gas liquid interface, it is also offering the negligible resistance, and the third one is through this liquid film, it offers major resistance or typically the rate limiting step here. Then bulk liquid of transport usually offers a small resistance. Liquid, fifth step, from the liquid to the cell surface negligible, across the membrane again negligible resistance, and intraparticle diffusion, if it is a pellet or clump, it is significant as you have discussed earlier in the case of intraparticle diffusion. but many times the microbial cells are suspended cells and not in the immobilized or in the pellet form. And then intraparticle diffusion to the reaction site, this is transport in the cytoplasm, it offers the negligible resistance. So, majorly we focus on step 3, that is diffusion through relatively stagnant liquid film surrounding the bubble, or you can say it is a gas liquid interface. So, we know the equation for the gas liquid interface as we have discussed in the mass transfer theory, particularly this convective mass transfer to film theory. So, it says rate of transfer is equals to KLA CAL star minus CL, and that should be equals to the rate of oxygen utilization Q naught into X. Now, how we can increase the rate of transfer, as I discussed briefly also, you increase the KLA, this can be done by increasing the agitation. So, this part how KLA is related with agitation, that part we will be discussing in the next lecture, where we will be discussing the power requirement in the agitation. Increase CAL, increase Q naught, or increase in the CAL star, increase in the oxygen demand Q naught, or decrease in the CAL. If you can decrease in the CAL, then also it, if you decrease CAL, then this driving force increases. So, it is very straightforward, you can see KLA should increase, CAL star should increase, Q naught should increase, at the same time CAL to be decreased to increase the rate of oxygen transfer. Now, following this last expression, this said KLA CAL star minus CAL equals Q naught into X. So, from here we can find the maximum cell density which will be supported by the given value of CAL star. So, it can be done if you assume CAL to be 0. So, what will be the maximum transfer rate? KLA A into CAL star, and this divided by Q naught, then X is replaced as X max. Further, we can also calculate what will be the KLA critical. So, if, as you know, this C critical we discussed here, C critical is on the x axis and this is related with the CAL. So, if you replace CAL with C critical, then we can calculate what will be the critical value of KLA. So, it says KLA into CAL star minus CAL critical Q naught into X. From here we can find the value of KLA critical. So, it becomes KLA critical equals Q naught X divided by CAL star minus C critical. And typically this is the critical value of C is about 5 to 10% of the air saturation. So, we will discuss a couple of examples here. The first is a strain of Azotobacter is being cultured in a 15 meter cube stirred fermenter for production of alginate. The volumetric mass transfer coefficient KLA under current operating condition is 0.17. So, KLA is given KLA as 0.17 second inverse. The solubility of oxygen is fermented broth is 8 into 10 to the power minus 3 kg per meter cube. Now, for part A it says if specific oxygen uptake rate is 12.5 millimole oxygen per gram cell per hour, then calculate the maximum cell concentration. So, for part A what you have to calculate is the X max. Cal star is given as 8 into 10 to the power minus 3 the 8 ppm kg per meter cube, and Q naught is given as 12.5 millimole per gram per hour. The X max, if you remember the formula, it says KLA Cal star divided by Q naught. Now, for part P it says after the start of culture, copper sulphate is accidentally added to the fermentation broth, which is inhibiting the bacteria growth. Inhibiting the bacteria growth means it is reducing the oxygen uptake rate. So, now it has become only 3 millimole oxygen per gram cell per hour. Then what will be the new maximum cell concentration that can now be supported with the same oxygen transfer. So, first we will solve the part A, then part B, only this Q naught will be replaced by 3 millimole oxygen per gram cell per hour. So, KLA is 0.17, Cal star is 8 into 10 to the power minus 3 kg per meter cube, and this X max, this is the we have to calculate. So, one option is we whatever solubility is given in the kg per meter cube, that we can convert into mole per meter cube. So, you divide by its molecular weight and kg multiply by 1000, it become in the gram. So, now it becomes 0.25 mole per meter cube. Similarly, this Q naught was in the millimole per gram per hour, we can calculate millimole per gram into per second. So, we divide by this. We have to convert into mole, to millimole to mole divided by 1000 and hour to second 3600. So, it becomes 3.5 into 10 to the power minus 6 mole per gram into second. Then we can put this value here and get the value of X max as about 12 gram per liter. So, we are getting the biomass concentration as 12 gram per liter. Now, typically if we just see this, it was 12, now it has decreased to 3, means close to 4 times decline in the Q naught, specific oxygen uptake rate. So, we can repeat the same thing here, this specific oxygen uptake rate was 3, we can again convert into mole per gram into second. Now, it becomes 8.33 10 to the power minus 7 mole per gram into second, and if you put the value here X max as KLA Cal star is divided by Q naught. Now, we are getting 51 gram per liter. So, this was close to 12, it has become more than 4 times higher. So, it says depending on the oxygen uptake rate, we can tune the cell mass density or biomass concentration inside a bioreactor. In the next subsequent slides, we will be discussing now the factors affecting the oxygen transfer in bioreactors. So, when you are supplying the oxygen, typically done through the bubble, and how the bubbles are created through the spurging, stirring, and depending on the media property. So, when you are spurging, there should be first bubble formation, then gas dispersion. Many times we see these two bubbles are combining together. So, bubble coalescence, then it also depends, transport also depends on the what is the viscosity of media, what is this stirrer speed and gas flow rate. Further, many times if you are seeing the aerobic fermentation, there may be foaming. So, we may need to use anti-foam agent that also affect the oxygen transfer rate. Further, temperature, because with the temperature the solubility decreases. In fact, this gas pressure and this oxygen partial pressure we have already discussed with the Henry law, that how the solubility is affected by both mole fraction as well as the total pressure. And in addition, the presence of cells and other macromolecules, because the cells have the specific requirement, because as we have seen in the table, the Q naught vary for different cell types. So, first if you are talking of the gas bubble, if there is a small size of bubble, it increases the interfacial area. So, if there is a more area, means there should be a more increase in the mass transfer rate. The typical size of bubble is about 2 to 3 millimeter. It forms a rigid surface, but when bubble size is more than 3, it forms a mobile surface. And if the bubble size is further very small size, to increase the further area, it becomes problematic in the viscous broth, or it becomes kind of a nuisance in the bioreactor. So, if you just see the typical bubble diameter recommended is 2 to 3 millimeter to balance both the surface area as well as the mass transfer rate. Next term comes the gas hold up. Gas hold up is defined as Vg, volume of gas bubble in the reactor, divided by volume of liquid in the reactor plus volume of gas in the reactor. And interestingly, this interfacial area is related with gas hold up divided by average bubble diameter dB. So, you just see the average bubble diameter is inversely affecting the interfacial area, and it is also affecting the, and this interfacial area is directly affected by the gas hold up. And typical value of gas hold up in stir fermentation is about 0.1 to 2. This is a typical value of the gas hold up. Further, in when bubble formation is done, the next is the sparging and stirring. So, there can be different type of sparger, porous, orifice and nozzle, and this affect the particularly the bubble shape and bubble size. Further, if mixing is done, then there is a impeller which causes the dispersion of bubbles. Here one thing is important to understand, that if gas flow rate is higher than the impeller dispersion capacity, then we say there is a gas flooding, means gas will go out of the bioreactor without getting dispersed inside the media. Further, the sparger location is critical, because there should not be the dead zone or dead pocket in the bioreactor. So, you can see there is a bubble formation, gas dispersion, in addition there will be bubble coalescence. Viscosity is affect, it causes the resistance to flow, and what is the stirrer speed and gas flow rate. So, this part, the bubble formation, you can have different type of sparger, porous sparger, a perforated pipe orifice sparger, nozzle sparger. So, basically it controls the bubble size. So, different sparger requirement that will be further discussing in the subsequent lecture, where we will be discussing about the agitation requirement. Agitation speed and gas flow rate. So, typically if you just see this KLA increases with stirrer speed and gas flow rate. For example, if I double the stirrer speed, there should be about 5 times increase in the KLa for the Newtonian fluid, and if I am doubling the gas flow rate, there is only 20% increase in the KLa value. Further, the high gas flow rate, there is a risk of impeller flooding as I discussed in the last lecture, and if there is excessive gassing, it can also cause the liquid blowout from the bioreactor. However, in the case of non-Newtonian fluid, the KLa dependence on the stirrer speed is weaker, and effect of gas velocity is similar to the Newtonian fluid. So, now when we are discussing the stirrer speed and gas flow rate, it depends on the fluid characteristics, whether your media is behaving like a Newtonian as well as non-Newtonian fluid. Next we discuss is the antifoam agent. Many times, particularly in the aerobic fermentation, there is a formation of foam, and that foam particularly it can go out of the bioreactor, causing the loss of media, loss of product. In addition, it can have this contaminated risk, outlet blockage, loss of volume, poor cell condition and cell damage. So, for this we keep 20 to 30% head space in the vessel to account for foam and gas holdup. Now, typically we use silicon based this chemical antifoam agent and they reduce the KLa value. So, how basically it works? It causes a reduction in the surface tension. You just see, if you increase the antifoam concentration, there is a decrease in the surface tension value, and parallelly if you just see, there is also decline in the KLa value. So, apart from chemical antifoam, there are other options. One can use mechanical foam breaker. They are preferred to preserve the liquid property. So, particularly they are high speed disc or centrifugal foam destroyer. So, what they do with the force, as soon as foam are formed, they break the foam or they remove the foam. However, it has a limited capacity, high power demand to operate this mechanical foam breaker, and if there is a heavy foaming, they are less effective. So, most of the time these chemical antifoams are used in commercial bioreactor operations, and this is the effect we have discussed, and it adversely affect the KLa value. And how it works? It works by minimizing the surface tension value. Next factor we have discussed is the temperature. So, as we know, if you increase the temperature, the solubility decreases. So, if you increase the temperature, the solubility decreases, and if solubility is decreasing, then delta C is also decreasing. It is a driving force. Further, this, if you just see, if temperature range is 10 to 40 degrees centigrade, KL increase outweighs solubility loss, but as the temperature increases move beyond 40 degree, the oxygen solubility drops sharply and there is a net decrease in the oxygen transfer rate. So, any typical bioreactor operation happens in this range 10 to 40 degrees centigrade. So, the balance point is the optimum temperature maximize, it should maximize the oxygen transfer without harming the microorganisms. And when you are talking this temperature, we can also discuss the gas pressure and oxygen partial pressure. So, we have already discussed this Henry's law. It says this solubility is proportional to the partial pressure divided by the Henry constant, and partial pressure is a function of total pressure into mole fraction. And this also we have discussed. If solubility of oxygen from the air is 9 ppm, then it will increase to 43 ppm if you are supplying the pure oxygen. This is in the air and this is in the pure oxygen. Next, we will be discussing the presence of other cells and different metabolites. So, one option is the cell presence affect the oxygen transfer, particularly through different organism morphology and the cell concentration, because oxygen uptake rate is directly proportional to the cell concentration. And if there is a complex morphology, particularly for this fungus or mold growth, they hinder with the bubble breakup. And in addition, when we are talking this interfacial blanketing, the cells protein and other molecule they can attach at the or they can adsorb at the gas liquid interface. So, macromolecule or smart particle on the bubble, it reduces the interface mobility and lower the Ka value. Further, they may also reduce the collision. In that case, it can have a small positive impact. Effect of interfacial blanketing is a system specific and varies with broth composition, and typically during the batch fermentation, changing concentration of the cell, substrate and product alter the viscosity and collision behavior. Thus, it clearly varies with time as this fermentation progresses. So, you just see the variation of KLa in a 300 liter fermentation using Streptomyces species. So, as the fermentation progresses, the KLa value also decreases because of the change in the substrate concentration, change in the cell concentration, change in the product, change in viscosity and collision behavior. So, with this I will stop here. So today we have discussed aeration part, particularly it is a part of gas liquid mass transfer. So, we discussed this, what is oxygen transfer rate and what is oxygen uptake rate, and importantly we discuss what is the critical oxygen demand, and followed by the we discuss what are different key factors which affect the oxygen transfer. Thank you so much.